Yeah, good evening. Myself, I'm Jumeir. Yeah, this is our quick five live sessions. In this season, that we discuss some problem related about our the manganese and lithium-based reagents and how that it's react with different kinds of molecules to produce the different kind of synthetic transformation in organic synthesis. That we will discuss all those things in our quick five lectures. Yeah, this is our the first question. This is our first question. That's our molecule. This thing called the bicyclic compound, then fused bicyclic compounds with the functional group of both the alkene. That's we have two different type of alkene. We call them double bond also, and that's halide group. That the aliphatic, that carbon bromine bond will be there, and in that presence of magnesium, simply magnesium and carbon dioxide, and in presence of that acidic work of that's we'll get a product. Along with that we are using auxiliary chloride. This one is nothing but the auxiliary chloride. And after that, the triethylamine also we are giving. Then what will be the expected product that we will expect this reaction? The options are that is a four kind of option. Then we can ignore the option. So whatever that A, B, C, D, that's why we have to solve that how this kind of product will be formed and what is that the final product we will expect in this whole reaction because we are using that the magnesium. Generally, that's whatever that you have the aryl halides like aryl halide that is reacts with magnesium. Then what we will expect? This one is our magnesium. Then what we will expect? The insertion, the metal insertion within that the carbon and halide bond. We will synthesize the organometallic reagent. This one is our organometallic reagent. We call them as the Grignard reagent. The scientist who discovered that this kind of reagent and we got them as the Grignard reagent. The metal insertion will be happen and this reaction is nothing but exothermic reaction. Exothermic reaction. Okay. Okay, because that's when you form that the Grignard reagent. Grignard reagent will happen that it will synthesize that heat will be result during sorry, about during that the reaction. The heat will be about that so we call them as the heat release that during the reaction and we'll get a the exothermic reaction of that. To control that heating within that the reactions also that's we are using the sometime ice bath to add that the aryl halide to that magnesium. Generally, what we will do to synthesize any kind of Grignard reagents that we have that's any aryl halide that we are taking that's aryl halides and magnesium. That we have that's what of that we are taking magnesium. Water magnesium that's we have that's we have heated that's in the under vacuum up to that the 300 degrees Celsius or more than that also that you can heat. So under vacuum only that you have to heat to activate that the magnesium tonics. That the magnesium tonics that is commercially available. As you take that magnesium in and in a sling tube, generally the reaction will perform in a called the sling tube that to avoid that the moisture or that the air atmosphere because the Grignard reagents these are quenched by that the moisture. So to synthesize the Grignard reagent, that we have to take care of that the moisture. And first that we are taking magnesium tonic and we have to be heated in a 3 degree 200 or 300 degree continuously up to that's 200 is like because the 30 minutes or the more than 30 minutes also okay. And after that we have to cool under the vacuum only, and then we have to add some amount of iodine to initiate that the green reagents are then we need to add some iodine followed by that the few drops of and that the or that we call them a few amount of RL halides or the any kind of halide that you should add. Then what will happen? Then this is reaction you will add, then you will give some external heating. The external heating is needed to activate. Yeah, the external heating is needed to activate our Grignard reagents. To activate the Grignard reagent. And what will happen? That's when you will give that the external heat. Then after some time when the Grignard will initiate it, during that time, the whatever the heating that you are giving, because of that only for the reflux will happen. But when that's your Grignard reaction will already initiated, it will start at that time that if you don't give any heat also, if you don't give any heat, and what will happen? That without the absence of heat also, that's during the formation of Grignard reagent, the, as this reaction is exothermic reaction, the reflux that within the reaction mixture also, if you don't give any heat also, the reaction mixture itself, that it will we call it as refluxing because of the synthesis of Grignard reagent. That is the only indication that you will know from where that your Grignard reaction will start. And the reaction will start and after that the rest of amount of RL halide that you just add. That the rest amount of RL halide or that the whatever that if it is RL or aliphatic halide, okay, then this salad you just add drop wise, either in the ice bath or even in the room temperature also sometimes that you can add to complete the synthesis of the Grignard reagent. And during all that the addition process, that you will see that the reaction mixture always refluxing without need of any external heating. That is that the indication, and that is that know that you will know that your reaction started. Sometimes also that you have to be careful that the quenching of that the backward reaction of Grignard reagent also sometimes will happen. That most of that things is only for some kind of like aliphatic kind of Grignard reagent. These are very sensitive as compared to aromatic kind of Grignard reagents. Okay. But in this reaction, what will happen? That's whatever our this one is with our carbon bromine bond, and that within that the bond the magnesium will insert and will get a Grignard reagent. That is kind of Grignard reagent, and this one is aliphatic, and somewhat that it is that the less that stable as compared to our aromatic RL halides. So that the aromatic Grignard reagent. That's why these are much more reactive. Okay. That's why these are much more reactive. So. And what will happen after that? Generally, who the Grignard reagent, whatever these are behave as a nucleophiles. These are the nucleophiles. Okay. Whatever that the R minus the MgH plus, this one acts as a nucleophiles. In this particular cases, this negative charge that will reacts as a nucleophiles to the carbon dioxide gas. That's why we have to purge carbon dioxide gas through a cylinder. Okay, that's why our the attack will be happen, and we will get CO minus. So whatever, and after that this protonation, that it will take a proton from this acidic source and we will get a carboxylic acid. That this is the synthesis of our carboxylic acid that we are expecting. Yeah, this carboxylic acid that we are expecting. And after that, what will happen? That we have auxiliary chloride. Thus, we know that from acid to that by using of auxiliary chloride, that we will get our corresponding what? Corresponding our acid chlorides. From this one, that we will get our acid chloride. That acid to acid chloride conversion, that is auxiliary, and also that you can give thionyl chlorides also. Yeah, this is SOCO2 also is possible. That if it is associated to that we can synthesize from acid to acid chloride. Okay. And also auxiliary chloride is also very good. Both one will. Okay. And generally what will happen that people are use that 1.1 or 1.2 equivalent of auxiliary chloride that is also sufficient to completely convert our acid to their corresponding acid chlorides. And after that, we have a base, that triethylamine, that we have that base. Because we have that alpha halohydrogen atom. And that halogen hydrogen atom, that will after the proton, that alpha proton, and followed by the removal of that's whatever our chlorine atom will be happens, and we'll get our corresponding that KT. This one is the highly reactive, we call them as the highly reactive ketene intermediate. Ketene, highly reactive ketene. Yeah, this one, highly reactive ketene. And these are highly unstable compound also. Choline is a highly unstable. Highly unstable and which are the highly reactive. So these are the and here that it will react to their corresponding that's we are giving. Then it will undergoes a 2 plus 2 cycle addition further to that this alkene as compared to our this alkene because this alkene is near to that call them as TT that is such a way that their orbital overlap will be more feasible as compared to our this one. And in this after that, then you will get a synthesis of this four member that cyclobutane ring that will fuse with our bicyclic ring. This is our bicyclic ring and the our four member bicyclic ring that will be fused with our cyclobutane rings. Okay, yeah. Now the whole process what actually what happened generally that first the Grignard reagent will be Hmm. What will happen in the whole process? The whole process, what will happen first, the Grignard synthesis will be happen, and along with that it reacts with our carbon dioxide gas, and we will get a corresponding carboxylic acid, and after that we have auxiliary chlorides, and we will get our corresponding acid chlorides followed by the in presence of triethylamine. We got a highly reactive that could be the ketene intermediate, and after that, this whatever our it will react with our corresponding alkene that will be present in our the bicyclic compound. Then we get our corresponding that 2 plus 2 cycle addition product as a final product. Okay, in the next question, what we have to what we will do that we have two different conditions that in presence of n-butyl lithium, simple that's with our the starting material and our also that the in presence of our others the n-butyl lithium, and we have used the termida as a chelatic ligands in the whole reaction that and in presence of ethyl ether and hexane also. Then generally the condition difference between that the both molecule is that in one cases we have that n-butyl lithium only, and in another cases that we have only that n-butyl lithium along with our the terminal ligand also that we are using. Then actually what will happen? Then in that the both cases that generally generally what will happen? That's it. Let's say that more acidic hydrogen that will be that's when we have butyl lithium, the more acidic hydrogen that will be extracted from the other lithium, and it will form their corresponding lithiated product. That by the but in that the in this cases that we have two different conditions, what will happen that in that the post this cases we have two different kind of hydrogen. You will see that we have two different type of hydrogen. This one and this one. This one is much more acidic hydrogen as compared to ours. This another ones. This hydrogen. This is Ha and this is Hb. But still, that in the first cases, the first one is undergoing the lithiation and we will get our corresponding lithiated product. But in that, the second cases, what will happen? That in presence of so what will happen that the second case is that in presence of strongly that we call them complexing the agent that the termida that we are using coordinated to the lithium atom and the and sorry coordinated with lithium with the nitrogen that is suppressed. That's why in the particular cases what will happen that the more acidic that hydrogen your methyl group is missing one. Okay. Sorry for that. Okay, that this hydrogen that will be lithiated and you will get your corresponding the lithiated in that the Hb position as compared to the H1. Why? And in the first cases, generally what will happen? The more acidic proton has to be the lithiated to the corresponding lithiated product. But in the first cases, what will happen? Because of this nitrogen chelation with that the butyl lithium, the lithium one, that's why it will first it will coordinate it. After that, the, whatever that the hydrogen that is near to that's that this nitrogen that will be abstracted by an n-butyl carbanion, that whatever is the strong base, and it will lithiated to their corresponding lithiated product. That is the only reason that's our Ha hydrogen that will be lithiated to their corresponding lithiated product. But when you are using that terminal ligand, what will happen? That terminal ligand first that will coordinate it toward the N-butyl lithium. Because of that only that because terminal is a that this one is nothing but terminal because in this terminal ligand we have two different nitrogen that will be coordinated to our butyl lithium. That's whatever the lithium that we have that it will be coordinated to our lithium one. Then what will happen? That there is no sites for that the binding of that the butyl lithium to their corresponding nitrogen, whatever the in the starting material. That's why that we call them as in present strongly complexing TMA, sorry, that the terminal ligands coordination of lithium with nitrogen in that the starting material that will be suppressed. That's why in that particular cases more acidic hydrogen that will be abstracted by a butyl lithium and we'll get our corresponding lithiated product. But in the fast cases, we don't have any that selective ligand. That's why first it will bind to our nitrogen one and we'll get our corresponding. Sorry, it will get our corresponding that the more acidic that the less acidic proton in this case that undergo the lithiated and we'll get our corresponding lithiated product. Okay, and in that the next questions that we have and this bicyclic compound like that, but in this cases, that we have hydrazone. This one is our hydrazone that in presence of N-butyl lithium. That's why using the particularly just mention my word. That's N-butyl lithium that we are using 2.1 equivalent in DMF solvent. Okay, that in DMF solvent. What will be that the final product that we have that variety kind is other option, but what will be that the final product what will happen? That's whatever hydrogen that will reacts with iron beta lithium and we'll get our corresponding the carbanion will get that the remove of the carbanion will get okay the carbanion because of the carbon negative charge that's will get our corresponding carbanion. How we will get? First what will happen? The whatever the butyl lithium that will abstract a proton from here, then it will form a corresponding the negative that one and even also that the another equivalent of the strong base and butyl lithium that will abstract another proton from here this one okay this proton whatever that proton sorry okay this proton that will be abstracted by L butyl lithium and will get our corresponding that the negative charge will get okay and after that what will happen that it will that undergo that since you have double bonds that we call them as conjugations or we call them as the resonance and the removal of tosyl group will be happen that in this so that will get a removal tosyl again also that this one will correspond to that living group in this reaction is nothing but nitrogen gas that will always that the call them as a driving force for this kind of reaction because that the nitrogen molecule that nitrogen triple bond that is more that stable molecule that's it's always that's always gives that the reaction and that the in forward reaction and these are that the driving force for this kind of reaction and we call them as this kind of reaction we call them as a Shapiro reaction type of Shapiro reaction and we'll get a carbanion and after that what will happen that's when you get a carbanion and after that we have that DMA N-methyl formamide. Okay. After that, what will happen? Then it will attack to our DMF and we'll get our corresponding that aldehyde, and this group will leave and will get our corresponding that formylation. Generally, what will happen? That's whatever we have. Sorry, that any kind of nucleophile that will attack to our DNA and it will give the corresponding carbonyl compound. Here, this is our corresponding carbonyl compound. That we will call them as the generally in formylation reaction. That these are our the formylation reaction we will get. And in the whole process, what will happen? That we will get a carbanion, that the alkynyl carbanion, we call them as the alkynyl carbanion. Alkynyl carbanion, and that will strongly nucleophile and that will attack to our DMF and will get the formylation of that the whole reacts. And now the next questions we have, and this is our next question. And the next questions we have this alkyne about that terminal alkyne, and we have that borane. You see, this one is our borane, the catechol borane. Okay, that in THA. And after that, we will get a product that's whatever the G1 in the intermediate will expect. And after that, we are using that the bromobenzene in palladium, the PPS the whole four that we call it tetrachis palladium, the triphenyl phosphine palladium. And in this palladium tetrachis triphenyl phosphine, the oxidant state of palladium is nothing but palladium 0. Okay. And we are using sodium carbonate and DME is sodium carbonate here is as the base. Okay. And DME, the solvent and the reflux we are using. We will get a product. What are the products that we are expecting? What will happen first? So whatever the any kinds of that alkene or alkyne, that's if it is alkene or that if it is alkyne, that will undergo a the any kind of borane reagent. Okay, that is the BH bond that whatever that borane that will undergo is radioselective addition to the alkene and alkyne, and you will get a corresponding the addition of that borane and hydrogen will be happening. If it is double bond, then the double bond will be there. Or if it is single bond, then single bond will be there. Sorry. And if it is a triple bond, then after addition, then you have a double bond in that your products also. And that if you don't have that the triple bond, instead of that the alkane, that's if you have alkene, then you will get this kind of addition will be happening. That the hydrogen and borane bond will be formed. Okay, and this one is always radioselectivity that you will get a more stable boron and whatever that the hydrogen and boron that will be add from that the same sites. That is same sites only that you will get the addition of that the hydrogen and boron because this that the nucleophilic the attack of that the alkene or alkyne to their corresponding boron is in a concerted manner. We call them as a concerted manner. That's why that it will only goes in that the same phases only. That's what about hydrogen and boron. And that's our boron that will be goes to that the less hindered side. So whatever the boron that will goes to that the less hindered side. Because of that the steric hinder, it has to go to that the less hindered side. Then we'll say that what will happen. That in the reaction what will happen then what will happen? That it will undergo to that alkyne, whatever the alkyne we have it undergo to the addition that we call it as 1 2 addition from the radioselective addition that we call it the radioselective that hydroboration reaction will be happen. He will see as whatever that this hydrogen and boron that has to be added from that the same phase. That it has to be added from the same phase because that's whatever that the hydrogen I told you that's boron and alkyne the carbon that is form a four-member chelating ring that during that the reaction. That's why it has to be added from That is the same phases only. Okay. Yeah. From that only they will decide the stereochemistry of our product. And after and then it will be undergo the radioselectivity to that whatever our boron that has to come to the less steric hindrance that instead of this one that is has to come that the other carbon. Okay. After the what will happen? That we have boron that this one is we call them as nothing but type of that the boronic acid. No, not boronic acid, we call them as boron, and that boron that will reacts with that the palladium and any kinds of the RL halides, the halide that and that X should be the bromine or iodine. Okay, it means that we call them as a base like sodium carbonate or the K2CO3 or that K3PO4 also that you can use sometimes. That depending upon your the static material of an product that you can use different kind of bases to promote that the coupling reaction that it will couple with R because the RL halide and we'll get our corresponding coupling product. But in this Suzuki coupling and this reaction called as Suzuki coupling and that will be discovered by the great scientist the Suzuki. And what will happen in this whole reaction, the retention of stereochemistry of our boron during their the migration or that the coupling of the phenyl bromide that will happen. The mechanism that we will discuss in palladium based reagent. But for general thing is that what will happen, that the stereochemistry of boron that has to be same during that the coupling. And you will get your coupling product as the same stereochemistry of your static material whatever that is boring. That's the thing that till now that you just remember this one, but how the mechanism will be happen, that will be I will explain in palladium based reactions. Okay. And in that the next questions that we have cyclohexanone, that we have cyclohexanone, and also that we have given reagent, that phenyl magnesium bromide in paratoluene sulfonic acid. And we have that's boron and PCC, and along with in the last cases we have metachloroperbenzoic acid. So what will be that the expected product that we are expecting in the whole reaction. Generally, what will happen that first, which we have magnesium bromide, that this one, that will attack to our that I told you that Grignard reagent that will behave as a nucleophile and that will attack most of the time that these are behave as a nucleophile. Sometimes that it will behave as a because of strong bases, but most of the time you will get as a product of strong that nucleophile as compared to the basic character. Then it will always, most of the time, maybe greater than 99% also, that it will behave as a strong nucleophile. And that will attack to your carbonyl group and you will get your corresponding that the primary alcohol or secondary alcohol it will depends or even also sometimes of that the ester also that it will react and you will get your corresponding keto products and also further reaction will be happen. It will depend the how much equivalent amount of that you are using and what is with the reaction conditions that whether you will get a keto or that further reaction will happen to their corresponding alcohol you will get. It will depend. Generally, what will happen? I told you that it will reacts with phenyl magnesium bromide in this reaction. That whatever that the phenyl magnesium that will sorry, it will attach to the carbonyl compound and we will get a O minus. That's whatever that O minus that we will get a that OMG. Okay, OMG Br. Okay, corresponding OMG Br that we will get. And after that, whatever what will happen that if you quench at the reaction and you will get your corresponding tertiary alcohol. And after that, you are using that the paratoluene sulfonic acid. That this one is acid, and that will after a proton. Sorry, that whatever our alcohol that will after a proton from paratoluene sulfonic acid, and it will create a carbocation. So whatever the carbocation you will get, like cyclohexyl, that carbocation you will get, and after the tertiary carbocation, okay, that's you will get a carbocation, and that will be stabilized by phenolic group, and also the two that the are the said that methylene group through hyperconjugation that it will be stabilized, and after that it will undergoes a that the elimination reaction we call them as a E1 elimination reaction, and it will undergoes, and you will get a corresponding alkene. That the more stable alkene you will get. This one is then a more stable alkene. Okay, and after that what will happen? That we have BS3 DMS, the dimethyl sulfide, also the Me2 is nothing but the dimethyl sulfide that we call them BS3 DMS. That will be react, and I told you that any kind of boron reagent that will attack, or we call them as that will add to the alkene or alkyne phases from the same phases only. We call them as a stereo specific in a stereo specific manner. That you will see how that in this particular case how that it will be joined. That suppose that this one is from the above side. That if you suppose, then you will get your hydrogen from the other boron. Sorry, and boron that will comes from the other side. And whatever the phenolic group has to be goes to the below sides, and whatever our hydrogen that is present that's in BS2 carbon that has to be in below sides. That's why we'll get a trans. As a trans boron, that's we'll get. Yeah, that is the other condition. But in this case, I'm not showing any stereochemistry, but these are the condition that you will get a stereochemistry that the trans addition, cis addition will be happen, but you will get a trans product. That is because phenyl, we are always looking for that the trans between that the different kind of substituent, not between that the boron and hydrogen. That's why we'll get a trans one. In this particular cases, that you will get a trans. And after that, what you have is that we have that the boron, and along with that we have that some oxidizing kind of reagent, and sometimes also that we are using that the we call them as a radiation type of reagent also that will depend that whether depending upon different kind of reagents that you will get from that boron to their corresponding products. If you use that hydrogen peroxide or in basing condition, and you will get your corresponding alcohol, and also that if you use that we have different kind of reagent. Sometimes sodium also, sodium and mercury that we are using, and that is zinc, and also that you can use. We have different kind of that condition. From that condition only that we will expect different kind of product. Then what will happen? That's we will get our corresponding this boron to their corresponding alcohol. And after that we are using that PCC, that you know that what is PCC. From that you know that what is PCC. No, no. From the first class that we have discussed that the problem related to PCC that will oxidize our primary and secondary alcohol to their corresponding ketone or aldehyde. Sorry, the corresponding aldehyde and ketone, respectively, because from the aldehyde only, from that primary alcohol to you can convert to their corresponding aldehyde, and sometimes also that it is corresponding the carboxylic acid also that it is possible to oxidize by PCC. But for secondary alcohol, it has to be oxidized to their corresponding keto groups. This one is the corresponding keto group that you will get. And after that, we are using that the MCPBA, that metachlorocorbenzoic acid. That okay. the metachloroperbenzic acid that we are using, and you know about the famous reaction that is nothing but what is the reaction that you will get a keto, and after that you know about Bayer village oxidation reaction. That's from that if it is that by using the different kind of oxidizing reagents that we call the metachloroperbenzic acids. In this particular cases, that will get our corresponding from keto to sorry keto to their corresponding ester, and this ester will be formed as you call them as a radioselective. The radioselective ester formation will be get, and also sometimes that if you are using alkene, it will oxidize to their corresponding epoxides. The oxidation also it is possible of the alkene to their corresponding epoxide by using MCPB, and also the keto to their corresponding ester will be possible, and this reaction will call them as the Baer-Villiger oxidation reaction. But in this particular cases, that will get a that the selectively that the one ester that instead of another ester. This is only why that we will get this ester. Why not the call them as the other ester? The reason is that that's when you have that the R O group and O group and whatever that the acid that we have, the perbendic acid, because when that's in the transition state, that's when you will attach that we call them as the migration will be happen to that the oxygen atom. Then what will happen? That the more electron rich compound that we call the more electron rich that site that has to be attached to that ring that we call the more more electron rich compound that has to be attached to that the oxygen atom, because that oxygen atom is electron positive. That to stabilize that the electron density on the oxygen atom, more electron rich compound. So the more electron rich that the group that will be migrated to the oxygen atom and will get our corresponding migrated product selectively. That's why in this particular cases, our more substituted carbon that will be as compared to that less substituted carbon, then our more substituted carbon that will be attacked and we'll get our corresponding the ester product. Whatever the ester product we have, we'll get our corresponding ester product. Okay, that is the only reason that why our more substitutes for the more electron rich carbon will be migrated. This is only because that in the transition state where the migration will be happen to that the oxygen oxygen bond, that's whatever the oxygen oxygen bond, their pi star bond. The whatever that the oxygen oxygen pi star bond that will be vacant, and that oxygen atom is that we call them as partially positive charge, and because of that only our whatever the group that will be migrated, that the more electron rich group will be migrated to that oxygen deficient atom to stabilize their electron positive charge, and will get a radioselective the answer. Suppose that if you contain a star the chiral center also, that suppose this phenyl group it has to be suppose that's about stacking metal has the reaction if the phenyl group is above, suppose that you will get a chiral ketone, and you will get a chiral that the ester also that with that we call them as the retention of stereochemistry throughout that the reaction. In MCPBA reaction, the retention of that the if there is any chiral center that will be present that already in your reaction, then you will get a corresponding that the we call them as retention of your stereochemistry or the that the of the chiral center throughout the reaction, and also in your product also your stereochemistry will be same as in your starting material. Okay, and what will happen in the next that the in the next question what will happen, that we have that keto, that's cyclic keto, then that's contain a the C, this one, yeah, that's we have the alpha halo of the other cyclopentadiol group. In this particular case, we have bromine. Anyway, now how we'll convert from that to their corresponding that the 1,3, the cyclic, that the diketone compound. You see, there is variety of methods, but that's whatever by using that the Grignard reagent, the how we'll synthesize that we'll discuss. There's variety of method also that you can synthesize. It is not that there's only one method is possible to convert from that the one starting material to their the other starting material. Then lot of method will be there for it. But the most appropriate method that people has to be used to use them, call them as the cheaper chemical, also as the not hazardous, is that we call them as normal reaction, we call them as the mild condition reaction condition, and without use of any kind of the explosive reactions also, that they try to avoid that kind of reaction, because people always want the mild condition reaction, and they don't want any other kind of the bicyclic, sorry, that the byproduct in that the whole reaction they expect. They always want the synthesis only one product. That's why people they have used that the most convenient method to get their corresponding product. But it will depend that in the other cases also. Sometimes also that it is not possible. Yeah, sometimes we call them as it is not possible to convert that the one static material to their corresponding product by using that the only one conditions only, because that's when you will transfer from that there's a some different kinds of functional group to the another functional group, then you have to be there is with a lot of option that how you will convert to from that. Suppose that you have alkene, then if you want to functionalize that alkene, then you can functionalize in a different kind of method also. And also sometimes that if you want to synthesize an alkene, then you can synthesize that alkene from the variety kinds of method, or it will depend that which method that will be much more convenient as compared to the other method. That will be much more easier that you will get your final product with a call them as a mild condition as compared to there are some vigorous that condition that you are using, and also there we call them as the yield also matter, and sometimes that the some byproduct also in some cases that if you are using that you will get a mixture of product that as compared to some particular kind of that the condition that will only gives a that the selectively that's only gives your product to minimize their byproduct in that the whole reaction, that will be possible. Okay, so in this case what will happen first, that's we have to use that the magnesium that to form their corresponding magnesium bromide reagent. And after that, that we are using manganese iodide, then you will see that the manganese iodide at minus 15 degrees Celsius. That because first we have to synthesize our okay. First we have to synthesize our Grignard reagent, whatever the Grignard reagent we have. Okay, the Grignard reagent we have first we have synthesized, and after that we are giving that the manganese iodide at minus 15 degrees Celsius. That is how we have to synthesize our Grignard reagent at 0 degrees Celsius. And after that we have to warm to that is the room temperature for that to complete that the complete synthesis of Grignard reagent. After that, that you just cool at minus 15 degrees Celsius, and then you just add manganese iodide. Then you will get your corresponding that the manganese iodide reagent. That in this first case that we have RMGX, that whatever the RMGX, that instead of that manganese that we have converted to their corresponding that manganese iodide one, and we'll get and after that we are using the acetyl chloride. This is nothing but that CH3COCl is nothing but we call them as a acetyl chloride. Acetyl chloride, and we'll get our corresponding 1,3 diketone. That's it. Suppose that if you don't use manganese iodide, then what will happen? That if you don't use manganese iodide, then what will happen? That it will form that's whatever that the diketone first. And after that, what will happen? That's whatever that the magnesium reagent that will attack to our keto group also, and you will get a some byproduct also. That's why first you have to make a less reactive reagent as compared to the greater reagent by using manganese dioxide to control there the reaction, to stop that the reaction at keto, not that the further reaction will be happen. Okay, that is the case is that you have to control that by using that the manganese added reagent, and you will get a corresponding final product as a 1,3 diketo. Okay. Okay. It will have name. Okay. So, okay. And this is our next questions. That's we have that ketone and also that the tosyl hydrogen in ethanol, and that we are using N-butyl lithium in THA, and also that the dimethyl formula. I told you that the DMF is nothing but a formulating reagents. And if you have strong nucleophile, then you will formulate a DMF. Sorry, that you will formulated that group to the corresponding aldehyde by using DMF. What will happen? First, it reacts with our keto groups, whatever the keto group, it will react and you will get your corresponding that hydrogen, and you will get a hydrogen. After that, we are using two equivalent n-butyl lithium. First, it will extract this nitrogen proton, and after that, what will happen? That it will extract a proton from this hydrogen, because this hydrogen is much more acidic as compared to the others hydrogen that will be present in that the ray. And also this one is same one. So that's if it, after that the another proton by using that another kind, sorry, another equivalent of n-butyl lithium, and you will get a carbanion, and that carbanion will undergoes that the resonance, and the tosyl group will be removed, that whatever the tosyl group will be removed, and again also that the removal of nitrogen group, and you will get your corresponding that carbanion, and whatever that carbanion that will attack to our dimethyl formamide, that NN dimethyl formamide. Okay, this one is given way, and it will attack, and our this group will be removed, and you will get your corresponding that aldehyde formation. From that this ketone, that ketone, then what we will got from the ketone to that alkene, and also that the extra carbon, and we will get as a formylation. That from the ketone, first it will converted to that alkene carbanion. This one is alkene carbanion, and that alkene carbanion undergoes a formylation with DMF. So reacts with the DMF, and it will form a the formylation of that alkyne carbon. Sorry, alkene carbanion. You will get your corresponding formulated product. And our answer is nothing but which one? Why guy? Like that we don't have that. In charge, so I'm in charge. Okay. I'm check whether someone is trying to joining or okay. Yeah, that is then the whole reaction what will happen? First it will form the hydrogen, and by using up two different kind of sorry, that the two equivalent of A and butyl lithium, that it will after this proton first this nitrogen hydrogen, and after that it will after the another proton, and followed by removal of tosyl group, along with the removal of nitrogen, and that removal of nitrogen, that is that driving force for that this kind of reaction, and we call them as a Shapiro reaction, and in the whole reaction you will get a carbon such as the alkene carbanion, and that will react with any kinds of nucleophile also. In this particular cases we are using DMF, and also that is sorry, that any kind of electrophile, and in this particular cases we are using DMF, dimethyl NN dimethyl formamide, and that will attack to the formamide, and removal of that dimethyl amine will be happen, the removal of dimethyl amine, and you will get a corresponding formulated product. Okay. And in that the next cases that we have that the chiral carboxylic acid that you see this one is nothing but chiral carboxylic acid and we are using this one is chiral carboxylic acid and we are using this one okay, as the N-methyl N-methoxy hydroxy hydroxylamine hydrochlorides the in presence of DCC and in the triethylamine the strong bases we are using and in DCM also not strong bases the fairly the good bases not strong bases as compared to like tertiary butoxides or that N-butyl lithium KHMDS or that is so NHMDS like that. Okay. Or that the phenyl lithium, or that the phenyl sodium also not strong that much, but these are fairly we call them as strong as compared to that some other kind of bases. And this reaction what will happen first? You see, is whatever the carboxylic acid, yeah, that will be reacts with this one that in presence of the DCC because this DCC that will activated our carboxylic acid and it will form a esters through by using of strong bases and after that the whatever that bases that we are using that will be that the after and that will remove that our hydrochloric acids in that the reagent and and you will get a that the N methyl and methoxy that's nucleophile and that nucleophile that will attract to our corresponding that ester that will be formed by our carboxylic acid and DCC and our that ester group will be removed and you will get a corresponding amide that this amide group you will get and that amide group will call them as the Winrep amide. Okay, this amide group we call them as the Winrep amide. Oh sorry, that's only whatever that is particular cases that one side is methyl and another side is nothing but the OMe. Okay, and methyl and methoxy. We call them as a Winrep amide, and that will be more stable amide as compared to the normal amides. Okay, that in the first step from the acid that will get our corresponding Winrep amides. And after that, what will happen? That we are using a strong basis. That is sorry, that the lithiated reagent that we are using, the in presence of THF and minus 78 degrees Celsius. And what will happen? This one is nothing but that the carbanion, and we call them as a strong nucleophile. Strong, very, very strong, because lithiated nucleophile are the very, very strong nucleophile, and that will be reacts with our Winrep amide, and it will be reacts and it will form a stable intermediate. Just see during that, that's when it will attack, and it will attack to a or will rep amide carbonyl group, the whatever carbon group, and it will form a that this five member ring chelated ring, and the chelated ring, an oxygen lithiation, lithium atom, that the chelation between oxygen and lithium that will stable our intermediate, and we'll get a five member chelated ring and that will be stable by our Winrep amides. And after that, it would do work up, then our N, Me and OMe group that will be leave and you will get your corresponding keto. Sorry, this one is nothing but aldehyde, this one is keto. That's you will get a corresponding keto. This is not alcohol, okay? Because after work of what will happen, the remove of this N, OMe and OMe group because it will gives this one, then you will get your corresponding that keto group you will get. Okay, that's and that's the whole reaction. What will happen? That from A that AC to that's we can convert that's from a AC. That's whatever that the acid that we have from acid to that's we can convert to their corresponding keto groups to that the whole reaction. You will see This one is our acid, and this one is our that keto groups. With that, the different kind of which kind of keto group that you want to do, that you can do. By first you have to convert it to the corresponding WinRAR amide, and after that, that you should use and different kind of organo, that magnesium reagent also it will be possible, and also that the organolithium. That most of the people they prefer that the organolithium as compared to that the organo magnesium reagents. Okay, and you can use that the organo magnesium also it is be good also, and also the organolithium reagent that will react with that of WinRAR amide to their corresponding ketone product. In that whole reaction that you will get a from acid to their corresponding that keto reaction through a medium called them as a WinRAR amides. That first you have to synthesize their corresponding WinRAR amide and you will get your corresponding keto. Okay, and this one is that the most of the people called them as the research people they have used that this kind of conversion from acid to their corresponding keto. Okay, okay, we take the next. And in that, the next questions we have, maybe that we have almost slides that I will check. Oh, 1, 2, 3, 4. Okay, yes, we have already there is the 4 slides, so we'll go faster. Okay, then in that cases, the, this is also nothing but a Shapiro reactions also, and we have that the tosyl hydrazide, that is presence of ethanol, and the two equivalent of N-butyl lithium as such, and we have that the DMF also, and we will get our corresponding that. So whatever in that the last also that I have discussed, this is a that the derivative one, that you will get a corresponding that aldehyde. But whatever that the alkene in that reaction will get here, that is you just see in that whole reaction condition that that this hydrogen will be abstracted as compared to the other hydrogen, because this hydrogen is this hydrogen and this hydrogen. Because of that, the stirring hindrance only, this hydrogen will be abstracted because there is no, because there is so much that acidic difference between this hydrogen and this hydrogen. But the steric hindrance between that this methanic group, okay, the CH3 group that will always that the avoid the proton abstraction from this quaternary carbon as compared to the sorry, the tertiary carbon as compared to the methylene carbon. That's why regioselectively that's we will get we call them as the regioselective that proton abstraction. The regioselective proton abstraction. And we'll get our corresponding carbanion and followed by our product we'll get. The whatever that products we have, that formulation product. In this case, that's why you have to see that's whether this product will get or that whether you will get this product. That's one that you have to fix. And also there is also possibility other than that this development also it is possible, but we won't get this development because of that the steric hindrance. Oh, okay, that in Shapiro reaction also that first you have to see uh, that how from the keto to how it will react to the corresponding alkene carbon, and also that you have to check that the regioselectivity from which sides your the alkene will be sorry that the carbanion will be formed, and you will check that after that removal of tosyl group and that nitrogen group will happen, and you will get your corresponding product. And this is a very good question that how you will convert it from that this starting material to their corresponding product by using that by using that whatever that the organolithiated that reagent, or that if you have any other kind of the idea also, that will be okay. Uh, that's first what that's what we'll do. That's part we'll do by using the lithiated reagent that in presence of Tomida. Okay. First we lithiated our this hydrogen. That's first we lithiated the carbon sp2 aromated hydrogen to the corresponding lithiated product, and after that we'll synthesize their boronic acid. First, what will happen? First, it will attack to that the borane, the trimethoxyborane. This is nothing but borane, OMe. This one also OMe, and generally borane as that we call them as the electrophilic. And whatever the nucleophile that will be attacked, and you will get your corresponding BOMe2. Okay, and BOMe and OMe. After that, if you give any that the HCl, that the concentrated HCl, or also that the aqueous HCl also, that's BOMe group, or also sometimes also ammonium chloride also sufficient to break that the oxygen methyl bond also. Sometimes that's one because it is also possible to break that from the dimethoxyborane to their corresponding boronic acids. Okay. Most of the time, boronic acids are that the powder compound, and these are moisture sensitive compound also. And also that you can keep is you can do the column chromatography for this compound because these are undergoes in silica gel. These are because they undergoes polymerization reaction. Undergoes polymerization reaction. That's why we can do that the column chromatography. Sometimes that you can do that if you do like that the has a flash chromatography, then you can purify. But most of the time, people during the whole reaction, they got that the boronic acid as a final product. Instead, they have used that's whatever that after that workup they got boronic acid, that you use directly in that the reaction without any further purification. And after that, what we'll do? That's we'll do the coupling. You see, that's we have this the two bromo that toluene and that will coupling with and the palladium TPS3 whole 4 in that the aqueous sodium carbonate and DME and reflux, and you will get a corresponding that coupling product. You will see this one is our the coupling product. And after that, we are using that the very strong bases, that LDA, as compared to the N-butyl lithium, that we are using LDA, that is much more strength. And it also even that deprotonated our CH3. Whatever that the CH3 that will be present in our benzene, and that even is possible to that for them as a deprotonate, and we'll get a corresponding carbonyl, and that carbonyl that will attack to our keto groups. Sorry, that amide group. That's whatever I told you. That the any kind of lithiated one that will react with our for them amides, or that you call them WinRAP amide, you will get your corresponding keto. That your nucleophilic attack will be happen, and you will get your corresponding keto. I will show you through mechanism. Okay, then first it will attack and you will get the lithiated intermediate. After that, what will happen? Then it will give the acid, then you will get your corresponding keto. And after that, what will happen? This one that we whatever the keto that will be present. That instead of keto, it will present as a enol because of that the stabilization of the whole aromatic ring, and that it will form a we call them as this one this for aromatic ring. To get that aromaticity that from the keto, that it has to be enolized, and you will get your corresponding that the anthracene, not anthracene, called phenanthracene, and the phenanthracene ring, that is phenanthrol. The phenanthrol ring that we will get. The anthracene we call them as that if you have This one is our benzene ring, and after that it will fuse another benzene ring, then we call them as naphthalene, and after that it will fuse another benzene ring, then we call them as anthracene. But if you fuse that another benzene ring here, that instead of there, then like in our products, then we call them as a phenanthracene, and that phenanthracene that we call them in this whole product that we'll get from that through that by using that the lithiated reagent and also that boronic acid coupling products, and after the LE also we'll get our corresponding phenanthra. Okay, that's the most important things. Ah, and this is our the next question. That's what will happen. That's we have that the RL bromides. This one, sorry. That's we have that the alkene bromides. That this one is alkene bromide, and that's we are using dot butyl lithium. Okay, that is the for the derivation of that the N butyl lithium. That's we are using a dot butyl lithium. And in pentane or in THA minus 70 degrees Celsius also, and we have that the DMF that I told you generally. That's what DMF. These are used as an electrophile for that the formylation reaction, and after the work we will get. Then what will be the expected product will get? In that whole reaction, that you will see a that we call them the driving force for the reactions also, that how that the driving force of the reaction will happen. Do get a, we call them as in the alkene also, different kind of alkene also will get. So whatever the product that you are expecting that you will get, along with also that you will get the different byproduct also, that the alkene byproduct you will get in that whole reaction. You'll see what will happen. That's whatever that's our dot butyl lithium that will undergoes a, we call them as a metal halogen exchange reaction, and we do that the carbon bromine bond, and we will get a carbon lithiated bond. And in this reaction we call them as the metal halogen exchange reaction. Okay, this reaction called metal halogen exchange reaction, and along with also that we will get a tertiary halides. And you just see that in the whole reaction that we are using 2.1 equivalent of that's the dot butyl lithium. First, what will happen? That's whatever our that the one equivalent that will undergoes first equivalent that is undergoes, and we'll get our corresponding lithiated product that the through metal halogen exchange reaction. And after that, that we are using and we'll get a byproduct from that dot butyl lithium to their corresponding tertiary halide. And then the next step that we are using, what is the DMF, the dimethyl formamide, and that will attack by our lithiated reagent, and we will get our corresponding that formulated product after workup, that we will get that this one will comes to the carbon, and this one will be leave, and we will get our corresponding formulated product. This one is nothing but that hydrogen will get. And in the whole reaction, your state, that's whatever that the stereochemistry that has to be written. The stereochemistry or of that alkene has to be written throughout the other reactions. Okay, stereochemistry has to be written, and you just see that we are using 2.1 equivalent. Then what will happen to that? The other kind of that we call them as the not butyl lithium. That it is only sufficient that so if you use that the one equivalent also, yeah, that will be sufficient for that whole reaction. Then why that's why we are using two equivalent? This is only because that you see that if you use this, yes. Oh, okay, okay, that's really. Oh, okay, okay. Oh, then you should say at least. I don't know. That's Okay. Oh, that's okay. Interesting. Maybe. Okay. That briefly I will explain. Then what will happen? That the whole reaction that we are using 2.1 equivalent of dot butyl lithium. Okay. Then what will happen? That by using a fast equivalent of that the lithiated reagent, first we will convert it to their corresponding lithiated, that the metal halogen reaction will be happen, and we will get our corresponding that the lithiation product, and also that our byproduct is nothing but tertiary halide will get from that dot butyl lithium. And if you use the n-butyl lithium, then you will get that the n-butyl bromides. And we are, and after that we are using that the DMF, that the dimethyl formamide, that this one, and n-dimethyl formamides. Okay, this nucleophile that will be attached to the formamides, and we will get that this intermediate, and after workup, that you will get your corresponding formulated product. The removal of dimethylamine, that we call them as a, the removal of dimethylamine will be happen, and you will get your corresponding formulated product. And you just see that in the whole reaction that you are using 2.1 equivalent of that butyl lithium, that instead of that, that we are using that the 2.1 equivalent of the butyl lithium, that instead of one equivalent also sufficient to get our product, but why that's why we are using one 2.0, we call them as a 2.1 equivalent, that the more equivalent why we are using, because that when you use the second equivalent normal, then you will get a alky. That this product also that, and it is it will be very easier to remove that the alkene as compared to the tertiary halides in their whole base. So that's why that they have used the two equivalent of toluene lithium to remove the this alkene. And generally this alkene is nothing but a gas also. If I'm not confirmed, but still, I think this alkene is a gas. To remove that gas in the whole reaction, that's why they have converted to their corresponding that the alkene. That is the only reason they have used 2.1 equivalent of the total lithium. Even that if you use one equivalent also, that you will get your product, that the formulated product you will get. And in that the whole reaction, what will happen? That's our from that this lithiated, that's whatever that lithiated one here, the whole reaction here, stereochemistry will be retained. Then whatever the stereochemistry, the whole reaction will be retained. And whatever the alkene you have, you will get that the same alkene. Then if it is Z, then you will get Z. If it is E, then you will get your ER. Okay. Do you have any questions? Okay. Yeah, to remove that, yes, yeah, to remove that alkene, today, that's why, because that alkene is a gas, okay, from the, yeah, gas are very much easier to remove. In that whole reaction, that if you have gas, that after the reaction, that it will already that remove from that the reaction, that you no need to separate. That's that's why people they have used two equivalent. But if you don't use that the two equivalent also, that you will get your product. Then you will definitely get your product. In that the sorry, that the next reaction that we are using LD as a two equivalent, and also that the paraformaldehyde, that's that maybe you know about the paraformaldehyde, and also our acidic work, but this is nothing but H plus. Okay, that the acidic work up, and you will get a product, the whatever the product we will discuss, and after that we are using reducing agent, and followed by that the iodine. Then what will be that the expected product will expect. Then first what will happen? That's by using LDA. That's the if you that instead of this that the chlorine, that if you have that is the bromide also, from that we call them as alkynyl. That alkynyl, that bromine or alkynyl chloride, that in presence of strong bases, that will that first by using of fast equivalent of that the LDA, that will abstract the proton, and you will get your corresponding alkyne. Okay, first by using of one equivalent of LDA, first you will get your corresponding terminal alkyne, and also that is the terminal alkyne has another hydrogen that another hydrogen, and that will be again abstracted by that another equivalent of LDA. You will get your corresponding alkyl lithiated products. Okay, that first it will abstract, and after that we have paraformaldehydes and our acidic workup, and we will get our corresponding. That's whatever the paraformaldehyde. These are nothing but a polymer of that the formaldehyde, and that whatever the lithiated reagent that will attack to our formaldehyde, and we will get our corresponding alcohol. After that workup only you will get your corresponding that primary, we call them as a propagyl alcohol you will get. And after that we are using that, you just see that the lithium aluminum hydride. Generally lithium aluminum hydride that it won't reduce alkane, but if you have that the propagyl alcohol I told you in maybe you remember or not I don't know, but during that the reduction the classes when I am taking, that I told you that it was the propagyl amine or the propagyl alcohol. It is possible by using lithium aluminum, we call them aluminum hydride, to reduce that sorry, that alkyne to their corresponding alkene. Okay, so to reduce their corresponding alkene, and selectively that will that you will get a the trans alkene. That this one is that you just ignore this iodine one. I will explain that how the iodine will come. That's when you will attack that the reduction will happen. First, what will happen? What drugs? Okay. That's whatever that this aluminum that will bind with our propagyl alcohol. That this alcohol group that will always that help to also that it will always help to reduce that our alkene. That's why normal alkyne that won't be possible by reduce through that the LH. But if you have that the alcohol that will bind to our that the lithium aluminum hydride, the coordinate with our call them as the aluminum, and after that that hydrate transfer, that whatever from the aluminum, the hydrate transfer will be happen to this carbon, and you will get a carbanion here. Okay, and you will get a carbanion, and that carbanion that will be reacts with our iodine, and we will get our corresponding that the we call them as RL, sorry, that the alkenyl halide, that the alkene, that highlight that if it is bromide or that if it is added, that will be possible because of this that the propagyl alcohol only that you can reduce your alkane. Yeah, that is the only reason that if you that if you use we call it only that's alkane, that's simply alkane, that you can't reduce your alkane by using lithium aluminum hydrides. And in that the whole there's the during call them as during hydrate transfer that you will get a chelated that the 5 member ring, and that chelated ring is much more stable also. That's why the reaction is thermodynamically favorable reaction. Okay, do you have any questions? Okay, and then the next reaction that we have that the selective sorry not symmetric ketone, that the normally the 2,2-dimethyl that cyclohexanol, and in presence of the tosyl hydrazide, sorry, the tosyl hydrazide, and in methanol solvent, and we are using that 2.1 equivalent of that hexane, sorry, that N-butyl lithium, and followed by the carbon dioxide gas and dilute aqueous HCl workup. First, and this reaction, whatever that I told you in that whole reaction also is that one. Okay, that this both condition is nothing but a Shapiro reaction condition. Okay, from that keto, from that keto to that you will get a alkene carbanion. The alkene carbanion you will get, and that carbanion that is be much more electrophilic. That we call them as a lithiated one. That the lithiated that alkene, and that will react with that any kind of recruitment that the electrophile, and you will get your corresponding that the electrophile and nucleophile that that will be joined, and you will get a synthesis of carbon-carbon bond or the carbon heteroatom, whatever that the bond will be happen. And in that the saturation, what will happen? That first it will form that the hydrogens, sorry, uh, from the T2 to the corresponding hydrogen, and first equivalent of butyl lithium that will abstract the proton from NH, and again that the another equivalent of that butyl lithium that will abstract a proton from here. Okay, then it will undergo the resonance. First, it will remove our tosyl group. Again, after that, it will remove our the nitrogen gas, and you will get a this kind of that the carbanion, and also in the carbanion also lithiated will be there because lithium ion that the lithium carbocation will be there, and that will stay as a lithiated one. We call them as a carbon like alkene, that lithiated alkene, and that will react with the in the first cases that will react with our the dimethyl formate, but in this cases we are using the electrophile is nothing but carbon dioxide. And this is a condition for that if you use DMF, then you will get a formylation. But if you use that carbon dioxide along with that the acidic workup, then you will convert it to the corresponding acid. Okay, these are the two different. If you use DMF, then you will get a corresponding aldehyde. That there are particular cases that if you use DMF, then you will get your corresponding aldehyde. But if you use that carbon dioxides or the and followed by the acidic workup, then you will get your corresponding the carboxylic acid. How that the carbon dioxide will react? That's whatever the nucleophile that will be attacked to the carbon one, and followed by you will get a the carbon oxygen negative charge, and that negative charge that will abstract proton from the HCl during workup, and you will get your corresponding the acid product. Okay, and in the next question, maybe so we have one more slide, so we'll go. That's we are using that TBS fluoride and that imidazole. This is nothing but a base. In the whole reaction we are using, and DMA which is a solvent, and also that we are using that TMS that CH2 that methylene TMS, that magnesium bromide. These are commercially available. People they are use this magnesium bromide. Also that you can synthesize also. And we are using that the oxalic acid in water, and also in the last step we are using a fluoride source. Fluoride source. Then a fluoride source they are using for the deprotection of any silicate. That people they are used that fluoride source as a deprotection of that the breaking bond between that the oxygen silicon bond that will be break by the fluorides too. That the that you can use that the different kind of fluoride like HF, and also the TBAP also that you can use. And in the whole reaction first what will happen that by using TBS chloride, first we have deprotect our alcohol group, and whatever the secondary alcohol we have, that will be protected by TBS chloride. That by using bases, the imidazole bases, that will be after the proton from this hydroxy group, and we'll get our corresponding protected hydroxy. After that, what will happen? That we have magnesium bromide reagent that will attack to our ketone group. Then you will see this ketone group that will be attacked, and we'll get a intermediate. This one, that will get a intermediate. And after that, what will happen? And we will get that. You know what is the this reaction? The name of this reaction? Yeah, yeah. From the Peterson olification, that you will get that the hexoalkene that you will get. And after that, we are using that the fluoride source, and that fluoride source that will deprotect our TBS group to their corresponding and that the alcohol. In that the whole reaction, what we will do that from a ketone to convert it to the other hexoalkene. So that the protection, deprotection, and that speciation or definition. The first that you have to convert it is by using that the TMS. That's why people they have used that TMS is also that to convert that the keto to their corresponding alkene also. And also there is other method is also possible to convert that the keto to their corresponding alkene also. That the other method also possible. That Wittig reaction also possible. But in some cases that people they avoid that the automatic reaction or competitive type of reaction. That's why they have not used that one. But these are also possible that if you use that any kind of if you want to synthesize any kind of natural product also, in that cases that you have variety kind of functional groups. So to avoid that the side reaction, yeah, that's why you have to be with the use that proper selective that the reagent the reaction condition to get your selectively on the that carbon will react to their corresponding that desired products. Okay, yeah, this one is our last question. Okay, that was the yes, we have that ketone and we have that the lithium reagent, and whatever that. Or in these cases, we have that the sulfur base, that lithium reagent, and we are using that the dilute aqueous HCl. And we are using that the MCPB also and POCl3. But in you just see that we are using 2.2 equivalent of MCPB. And also the N-butyl lithium and formaldehyde and acetic anhydride after that, after that we are using the sodium and sorry, the sodium in mercury, the are also the methanol and ethyl acetate. Okay, that's we have eight condition. And what will be that the expected product? After that, the eight process. And then that if you process from that the one step to eight step, that in the whole reaction that you will get that overall that the 5% yield, that 10% yield you will get. That we call it, even if you are in the whole step, in the every step, the, that if you got that the more than 70% or 80% yield also, then in that we call them overall from the first step to eight step, that you will get only that the 5% yield. That if you start from that the 1 millimole, then you will get that the 0.05 millimole as a final product. That after eight step. Okay, that's why that's if you do for by using different kind of reagent, and if your the reaction does not have that much very good yield, then because there is excellent yield, then you will get very little less amount of it. So better that by using that the proper kind of reagent to get maximum yield. That's why that you have to be that if you want to planning for the 8 or 9 step synthesis, in that cases you have to be very careful about your reagents. First, what will happen? That's whatever our this HA reagent that will be attacked to our keto groups, and after that, so whatever our that acidic source we have given, and that will be converted to our corresponding hydroxy group. Okay, the whole reaction, and we are using the two equivalent of this we call them as that MCPB, and that MCPB that by using of two equivalent of metachlorophorobenzenic acid, that will converted our that the sulfur to their the corresponding SO2 by oxidizing our sulfur to their corresponding that the SO2 pH group. Okay, because that we are using 2.2 equivalent. That if you use only one equivalent, then it will only convert from that sulfur to sulfur oxide. Okay, that's the one. If you use that another equivalent, then it will convert it to their uh, sulfur oxide to their corresponding this one. Okay, that's why people they are using that 2.2 equivalent. After that, you are using that POCl3 pyridine. What will happen first? That it will whatever our tertiary alcohol that will binds with our we call them POCl3, and after that, because the first it will for a living group who reacts with our the we call them the phosphorus oxide trichloride, and in presence of strong bases, that's whatever that's that pyridine that will after that proton, and he will get a we call them as E2 elimination by the removal of that the O and P, that part of the bond will be formed between O and P, and you will get a your corresponding alkene. That this alkene will be formed. In that the whole reaction, what will happen from the first step to fourth step? In that the first step, the nucleophilic atom will be happen, and after that the protonation, that you will get your corresponding hydroxyl group. And then the third step that we did from the sulfur to that the sulfur dioxides. Then you see this one your corresponding sulfur dioxide by using metachlorocarbonic acid as a 2.2 equivalent. And after that, the E2 elimination will be happen and you will get your corresponding alkane. That the more substituted alkane you will get. And after that, we are using that we call them N-butyl lithium, and this one is our the N-butyl lithium. So sorry, that N-butyl lithium we are using 1.05 equivalent, and whatever that the proton that will be adjacent to our sulfur dioxide, that phenyl sulfur dioxide and our alkene group, that one is much more that we call them the acidic one, and after it will form a carbanion that will be we call them as, yeah, I will draw. Okay, this carbanion, okay, this carbanion that will be stabilized by the resonance with this one also, and also the resonance between the both oxygen atom. That's why this hydrogen is much more called acidic that as compared to the other hydrogen. That's why it will after that proton and it will form a carbanion fast. Okay, after I will draw everything. Yeah, this hydrogen that will be attracted by n-butyl lithium, and you will form a carbanion here, and that carbanion will attack to our benzaldehyde. Okay, and you will get a corresponding O, that pH, and after that whatever that the negative charge that will be formed by that the oxygen atom after that attack, and you will get a corresponding with that the acetic anhydride. This is nothing but our acetic anhydride, structure of acetic anhydride. Okay, and whatever the oxygen negative atom, yeah, that will be attacked in here. That methanol group will be removed. That will not methanol. That the this O minus group that will be removed, and that will after add a proton, and and you will get a that the acetic acid after that. Okay, CH3, sorry, that the CH3COOH. After that, the removal of that this methoxide ion that you will get, so that the no, not methoxide, and not know that the term for that one. But after protonation, you will get a byproduct as a your acetic acid, and in that whole reaction, that what you did that in the ortho position of that sulfonyl group, that you will join a, we call them as the acetyl through the N-butyl lithium, benzaldehyde, and we call them acetic anhydride. After that, we are using that the sodium and methanol and ethyl acetates, and you will get you know that the name of this reaction. Do you know that what is the name of this reaction? Yeah, Julia olefinasa reaction. The- like that Peterson olefinasa reaction, that you will get a Julia olefinasa reaction. In Peterson olefinasa reaction, what will happen, that you will get a Z alkene, but in Julia olefinasa reaction, that you will get a E alkene. Okay, that in sulfur based reaction we will see, but for your to know about that the general thing, that in Peterson olefinasa that you will get Z alkene, but in Julia olefinasa that you will get a E alkene. Why? That in Peterson olefinasa reaction, that you will get a radical anion, and that radical anion has to be stabilized because that radical anion is also stabilized to radical anion. That's why it always gives a that the thermodynamically favorable that alkene. But in Peterson olefinasa reaction, that you will get a four member ring of that the silicon or oxygen bond. After that, the cleavage of that the short four member rings of that silicon oxygen bond, and you will get a corresponding alkene, and that's alkene is because they are stereospecific. That reaction is stereospecific, but this reaction is particularly that we call them as a stereoselective. And you will get a selectively that the E alkene, that instead of here the Z alkene. You will see if you want to check also the mechanism also you will find in Julia olefinasa reaction. The Julia olefinasa reaction you will get the always we call them as E alkene. Okay. Yes, yes. No, that's you will only get that one isomer. Yeah, that package of that the four member ring, like then whatever the silicon and you have, then you will get a that majorly that you will get a one isomer. It's not like that you will get one because that whatever that the silicon oxygen bond, this bond will be break because from that one this bond will be break and that you will get a corresponding alkene. It's not like that this bond will go and you will get a that's why in the speeches on olefin case most of the time you will get a selectively one alkene. But maybe that you will get that some amount of for them as uh, that the byproduct. It's not byproduct the that the other alkene also you will get, but I'm not confident. But whatever up to my knowledge that I know that you will get a selectively one product so repetition and and whatever the concern you have that's in assignment 3 that's you have raised a concern in the last class I told to my that the seniors yeah, that's what they have checked that the assignment they have corrected that's as per your request they have corrected one so you just check okay the assignment that you can check also yeah they have corrected that assignment okay thank you for your that checking that you because of you only they have checked okay yes yeah definitely the score will change don't worry okay that yeah this is my like that last slide so that if you want to have that any question you can ask it's not a problem okay you can share the screen also okay yeah visual okay 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 today I will check and I will inform you because the whatever the week is that the assignment solution also they will give in okay don't worry the assignment solution also they will provide you. And if you have any concern also that you can say in classes, okay. That is yeah, I will note down for the wait. That's note I will note down. Okay, good. Okay. Week 4, question 3. Yeah. Yes, yes. Okay. Then you just ignore that. Okay, don't worry, I will stop the recording also.